Hello, chemists. This is Miss Placino, and you are watching Screencast 4.5 on hybridization. This screencast is going to be different from previous screencasts because I'm not going to walk through a PowerPoint presentation with you. We're just going to talk about the practice problems. Hybridization is an advanced topic, and it is challenging. It can be really difficult for students to visualize and kind of pin down exactly what's happening. The whole point of hybridization is just to help scientists explain what type of bonding is observed. If we take a look at carbon with its 6 electrons, we would predict an electron configuration that looks like this: 1s2, 2s2, 2p6. If we were to draw out the 4 outermost electrons from the the 2s and the 2p sublevels, we would get this as carbon's Lewis dot diagram, where the 2 s electrons are paired up, and then the 2 p electrons are going to be in different orbitals, so they'll be unpaired. That diagram makes it look like carbon is only going to form 2 bonds and isn't going to complete its octet. That is not the case. We observe carbon forming 4 bonds. So scientists came up with this hybridization theory to explain what's going on. And they say that the s orbital and the 3 p orbitals are going to mix together to create what they call hybridized molecular orbitals. And instead of having essentially a pair of electrons and 2 unpaired electrons, when we hybridize, we'll get 4, they're called Sp3 orbitals. We'll put one of those electrons in each. Now all of a sudden we have a Lewis diagram that looks a lot more in line with what we see carbon, or how we see carbon behaving. So that's all this is. It's just a theory to help explain why we get the molecular shapes that we do. I'm not going to really pester you too much about the theory behind it. I just want you to be able to apply it. So you're going to be asked to predict the type of hybridization that has occurred in certain atoms. And really, we've got a shortcut that can work, and it comes down to, can you count? By this point in the semester, I feel really confident that all of you are very, very good at counting. So let's talk a little bit about this shortcut and how we're going to apply it. Count the number of atoms and unshared electron pairs that are attached to the atom of interest. You can see from the practice problems, we're going to be looking at bigger molecules, so I don't want to just say the central atom. We're talking about things that are attached to that central, or the atom in question. We're talking about other atoms and unshared electron pairs. So if there are a total of 4 things attached, the atom must have Sp3 hybridization. In other words, 1 s and 3 p orbitals were mixed together to create it. If there are a total of 3 things attached, the atom must have Sp2 hybridization, an s and 2 p orbitals. If there are just 2 things attached, the atom has Sp hybridization. Please remember that you want to treat single, double, and triple bonds as though they are all the same. The number of atoms bonded to the atom of interest is important, not the number of electrons between the 2 atoms. So again, we're counting things attached to the atom of interest. Those things can be other atoms, or they can be unshared pairs. If it's another atom, it doesn't matter how the 2 atoms are bonded together. So it doesn't matter if it's single, double, or triple bonds. It just matters that there's something else attached to the atom of interest. So let's try this out. I think it'll be easier to apply than it is to try to explain. First thing I want you to do is go through and count sigma and pi bonds. Any place you have a single bond, that has to be sigma. Any place you see a double bond, we know that it is a sigma and a pi, and triple bonds are 2 pi's and a sigma. So let's just go through and count. I'm going to get my sigma bonds first. I see 1, 2, 3, 4, 5, 6, and in a double bond, one of them must be a sigma bond. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. There we go, I lost track. And my pi bond is from this double bond. I just marked it in blue, so I have 1 pi bond. Great. Atom number 1, and I'm going to erase all these other little things that I've put on there as I kind of made a mess, is this oxygen atom. I see a total of 1, 2, 3 things attached to that oxygen, the 2 unshared pairs of electrons and a carbon atom. So if I've got 3 things attached, that has to be Sp2 hybridization. In this case, the geometry that is observed, well, it's just 2 atoms bonded together. So it's a linear geometry. Let's look at atom number 2. Atom number 2 is this oxygen atom. I see 1, 2, 3, 4 things attached to it. If I've got 4 things, in this case 2 atoms bonded to it and 2 unshared pairs of electrons, I have Sp3 hybridization. It's a little bit more complicated from a geometry perspective. The way it's drawn, it looks like it's a straight line, but think about molecular geometry. I've got 2 atoms bonded and then 2 unshared pairs of electrons. That's going to be the bent geometry. And finally, atom 3, that's the carbon. It's got a carbon atom bonded to it and 2 oxygen atoms. So I see 3 things attached to the atom of interest. So that must be Sp2 hybridization. I've got no unshared pairs of electrons on that carbon. I've got 3 things bonded to it. That is a trigonal planar geometry. Hopefully, by kind of just breaking it down by to how many things are attached to the atom of interest, that's going to clear things up a little bit. Why don't you pause the video and try out the second molecule? Let's walk through this one together. I see a total of 8 sigma bonds and 1 pi bond. Atom 1 hybridization. It's got 4 things attached to it, therefore it has Sp3 hybridization. I've got 4 things attached to the atom of interest with no unshared pairs. That's going to be a tetrahedral geometry. Next up comes nitrogen, atom number 2. I see 2 carbon atoms bonded to it and an unshared pair of electrons, so 3 things. Oops. So that must be Sp2 hybridization. This is a geometry that we did not talk about explicitly. If you take a trigonal planar and you pull off one of the bonded atoms and you replace a pair of unshared electrons, you get another variation of the bent geometry. That does not come up too frequently, so if you couldn't figure that one out, don't stress. And finally, we have oxygen, atom number 3. We've got a total of 4 things attached to the oxygen atom, 2 atoms and 2 unshared pairs of electrons. So we must see Sp3 hybridization. And again, it's very similar to atom 2 up in the previous question. Don't be fooled by the fact that it's drawn like it's a straight line. It's not necessarily going to look like that. We've got 2 unshared pairs of electrons, 2 bonded pairs. That also corresponds to a bent geometry. Pause the video and try out the third molecule. Check your work. I've got 6 sigma and 3 pi bonds. Hybridization around the nitrogen is Sp, just 2 things attached to it, another atom and an unshared pair of electrons. Therefore, it's going to be a linear geometry. In the case of this carbon atom, I again have 2 different things attached to it, a carbon and a nitrogen atom, so Sp hybridization. And yeah, no unshared pairs of electrons on the carbon, it's going to be linear as well. The last atom in question is that carbon atom all the way to the left. I see 2 hydrogens bonded to it and a carbon, so that's a total of 3 things attached to that carbon atom in question, so that must be Sp2 hybridization. And from a geometry perspective, I've got 3 things bonded to the central atom with no unshared pairs of electrons. That's going to give me the trigonal planar geometry. Okay, I'm going to leave that last one for you to play around with. You, of course, should check your answers online. Hopefully breaking it down just in terms of how many things are attached to the atom is going to make the idea of hybridization, or I should say the application of hybridization, a little bit easier. Don't stress too much. I'm not going to really try to crush you with this stuff on your test, but you can pretty much guarantee that I'm going to give you a molecule like this and ask you to tell me about hybridization as well as geometry. So keep on practicing. You've got this one other problem and your quest homework to play around with. I hope this was helpful, and I'll talk to you again soon.